Metallic flop and directional color shift are among the most critical appearance defects in automotive coatings because they directly influence perceived quality and customer satisfaction. Unlike surface texture or chemical defects, these issues are purely optical, arising from the orientation and alignment of metallic or pearlescent pigments within the coating film, their interaction with incident light, and the subtle influence of application, flash-off, and curing parameters. From an OEM RD&I perspective, controlling metallic flop is not about guessing pigment behavior. It's about managing the physical distribution of flakes, film formation kinetics, and visual consistency across every panel. Visually, metallic flop manifests as areas of inconsistent reflectivity or color intensity when the panel is viewed from different angles. A panel may appear perfectly uniform at a direct viewing angle, but reveal lighter or darker regions when tilted, rotated, or observed under shop lighting. Directional color shift is closely related, where a panel transitions across the spectrum due to flake orientation or base coat interference pigments. Under magnification, properly oriented metallic flakes lie parallel to the substrate, reflecting light evenly. Flakes that have tilted, overlapped, or are irregularly distributed create localized variations, leading to the perceived optical defects. These variations are subtle, but easily detected in OEM visual approval labs or by discerning customers. The fundamental mechanism of metallic flop begins during application. Metallic and pearlescent pigments are plate-like or rod-shaped. Their reflective properties are highly directional. The shear forces generated during spraying, atomization, and impact with the substrate determine the final orientation of these flakes. High atomization pressures or inappropriate nozzle configurations can cause flakes to tumble or stack, leading to inconsistent flop. Similarly, the viscosity of the base coat plays a decisive role. Low viscosity systems may allow flakes to sink or float during flash-off, disrupting uniform alignment. High viscosity systems may resist flow, preventing flakes from lying flat and causing local misorientation. OEM plants often measure viscosity at multiple temperatures to ensure the coating maintains optimal flake mobility while preventing sag or orange peel. Film build is equally critical. Uneven DFT across horizontal, vertical, or curved surfaces creates areas where metallic orientation varies. Thicker films may trap flakes in unfavorable positions, while thinner regions may expose the substrate color too strongly, amplifying perceived flop irregularities. OEM technicians routinely use non-contact DFT gauges and mapping to identify potential high-risk zones before curing. Flash-off time and solvent balance also directly impact flop. Proper flash-off allows the film to remain open long enough for metallic flakes to self-level under gravity and surface tension forces. Too short a flash-off traps flakes in random orientations, while excessive flash-off may allow surface skinning that restricts pigment mobility during oven ramp. Additives provide subtle but essential control. Flow and leveling agents influence surface tension gradients, allowing flakes to slide into parallel alignment. Anti-settling agents prevent flocculation of pearlescent pigments during storage and application. However, overdosing these additives can stiffen the film prematurely, reducing pigment mobility, while underdosing leaves flakes uncontrolled. Surface active additives are also used to optimize wetting, ensuring uniform pigment distribution across complex geometries and avoiding localized clumping that leads to visible flop anomalies. OEM labs carefully titrate additive levels for each formulation to balance flow, leveling, and stability without introducing secondary defects, such as cratering or orange peel. Environmental conditions during application can amplify flop issues. High booth temperatures accelerate solvent evaporation, creating rapid skin formation that locks flakes in non-optimal orientations. High humidity can slow evaporation, causing flakes to sink or cluster. Consistency in temperature, airflow, and relative humidity is therefore a key factor in high-volume production. OEM plants typically monitor booth parameters continuously and adjust spray parameters or solvent blends to maintain consistent flake alignment. The interaction between metallic flakes and pearlescent pigments also affects directional color shift. In multi-layer systems, interference pigments rely on precise film thickness to generate the intended spectral effect. Variations in DFT, flash-off, or solvent reflow can alter the optical path, creating unexpected color shifts. Base coat formulation, solvent volatility, pigment type, and particle size distribution must all be optimized together. OEM RD&I engineers often perform trial panels under controlled environmental conditions to establish process windows that guarantee target flop and color behavior. Troubleshooting metallic flop requires a structured approach. First, verify film thickness and uniformity across all critical areas. Second, examine spray parameters, including atomization pressure, nozzle type, and distance, ensuring they are appropriate for the pigment type and size. Third, analyze viscosity and solvent balance to confirm that the film remained open during flash-off for optimal pigment mobility. Finally, evaluate additive selection and dosage to ensure flow, leveling, and wetting are optimized without introducing secondary defects. Panels that fail visually but pass gloss measurement often have subtle misalignment of metallic flakes, which is detectable only through multi-angle inspection or OEM flop measurement systems. The key takeaway is that metallic flop and directional color shift are not defects that can be solved by guessing additive levels or arbitrarily changing spray technique. They are the result of controlled pigment alignment during application, flash-off, and early bake, influenced by viscosity, film build, solvent balance, environmental conditions, and additive selection. Properly managing these variables in a systematic way eliminates inconsistencies, ensures uniform optical performance, and meets the strict visual approval standards expected in OEM production. If you've experienced panels with uneven metallic reflection, inconsistent color shift, or unexpected flop, leave your questions in the comments. Future episodes will dive into real OEM plant cases showing multi-layer metallic and pearlescent base coat solutions, including troubleshooting tips for mottling, haze, and DOI issues that often follow improper flop control.